Hey everyone, and welcome to the lecture on Chapter 6. Chapter 6 involves a lot of math. We're going to be talking about the composition of chemical substances, of compounds. And so we will be talking about that composition mathematically. So the first thing is actually a little bit of a review or touching on some details, differentiating between formula mass and molar mass. So formula mass is really the mass of one molecule of a formula or one formula unit of an ionic compound. So you should know how to do this. We've talked about it already. So for chloroform, for example, this is the chemical formula, CHCl3. So there's one carbon, and carbon's atomic weight is 12.01 atomic mass units. And there's one hydrogen. Hydrogen's atomic weight is 1.08 atomic mass units. Sorry, that's a mess, but AMU. And then chlorine, there's three of them. That's what that subscript 3 means. And chlorine's atomic mass is 35.45 AMUs, or atomic mass units. So we're going to calculate these totals and add them all up, sum them together. 3 times 35.45. And these are all in atomic mass units. So our total here of 119.37 atomic mass units. So formula mass is in atomic mass units. We added up the mass of all of the atoms. All right. You are familiar with doing this because this is what we've been doing to calculate molar mass. Molar mass is the same number, but the unit is different. The unit is going to be grams because that is how we calculate the mass of 1 mole of a substance. In fact, if I were to calculate this for you, if we take 1 molecule of CHCl3, which is chloroform, and it is 119.37 atomic mass units, and we want to convert that to grams, we want to convert that to, we want to know how many grams is 1 mole of this substance. First, we need to multiply it by a mole. So 1 mole of anything is 6.022 times 10 to the 23rd per mole. And then if we want to convert the atomic mass units to grams, we need to use the conversion factor for that. And guess what it is? 1 gram is 6.022 times 10 to the 23rd atomic mass units. All right, so these numbers end up canceling out, as well as our atomic mass units. And so essentially, if we were to run this conversion math, we would end up with 119.37 grams. So we typically don't do all this math. We simply add up all of these components and we change the units from atomic mass units to grams when we are using molar mass. So you may have some problems in the homework that ask you to determine the formula mass or the molar mass. The only difference between the two is the units, but the way that we calculate it is the same. We're adding up all of the atomic masses of all the parts. Okay, so the next little piece of math that we're doing is learning how to calculate percent composition. So we might write this as percent composition, or sometimes it's called percent mass or percent by mass. All right. And so the formula for this, I'm just going to use a different color. All right, the formula for percent composition is, it's the mass of an element divided by the mass of the compound. Times 100% to turn it into a percentage. So the percent composition, I'm going to actually change this to the percent composition of a certain element. So you'll see in the example questions, it'll say what percent of this element is hydrogen or whatever. So you'll be calculating the percent composition of each element. All right, so we can do this from experimental data. In fact, this is how the chemical composition of different compounds was initially discovered, from some chemist breaking it up into its different compounds and calculating the percent composition. So let's do this first example problem. A 10-gram sample of gas is shown to contain 2.5 grams of hydrogen and 7.5 grams of carbon. What is the percent composition? So we want to know what percent is hydrogen and what percent, is carbon. So for the hydrogen, the percent hydrogen is going to be the mass of hydrogen. So the mass of hydrogen on the periodic table is 1.008 grams per mole. And, spacing out here. Let's erase that. The mass of hydrogen in this experiment, all right, is 2.5 grams. And the mass of the compound, the total sample, is 10.0 grams. Multiply all that by 100%, and we get 25% hydrogen. Carbon we've got 7.5 grams of carbon out of the 10 grams of the sample. So in this case, carbon makes up 75% of the mass. Notice that these two add together to be 100%. All of the components need to add together to be 100%. That's sort of the definition of percents. All right, so we can also figure out the percent composition if we are given the molecular formula of something. So for example, what is the percent composition of NH3? So it's asking what is the percent nitrogen and what is the percent hydrogen. All right, so in this case, we'll use the periodic table masses. So first, we probably want to figure out what is the mass of NH3 as a whole. So in NH3, ammonia, we have 1 nitrogen, 14.01 grams per mole. We're figuring out the molar mass here. And hydrogen, we have 3 of them, 1.008 grams per mole. So 14.01 plus 3.024 is a molar mass of 17.03 grams. All right, so if that is the case, then the mass of nitrogen is, in this compound, 14.01 grams for every 17.03 grams of ammonia. And the hydrogen, there's 3.024 grams of hydrogen for every 17.03 grams. And we do the math, and that percentage of nitrogen turns out to be 82.27%. And the percent hydrogen ends up being 17.76%. Again, those numbers add up to 100, in this case 100.3%, because there's a little bit of error there with rounding. But again, they should add up to 100%. It's a good way to check that you did your math correctly, because if they didn't add up to 100%, you did something incorrect. All right, let's try another one. This lecture is going to be mostly lots of example problems. Eek. All right, calculate the mass percent of chlorine in Freon, which is a cooling agent used in refrigeration. And this is the chemical formula for Freon. All right, so the first thing we need to do, since we're given the molecular formula, is figure out the molar mass. So I'm just going to list out all of the elements here. There's 2 carbons, and carbon's atomic mass is 12.01 for a total mass of carbon 24.02 grams per mole. Chlorine, there's 4 in this molecular formula. So 4 times 35.45 grams is 141.8 grams per mole. And then fluorine, there's 2 of them. And the atomic mass of fluorine is 38.00 grams per mole. Oops, sorry, it's 19. 19.0 grams per mole. So times 2 is 38.00 grams per mole. So the molar mass of Freon is 203.8 grams per mole. I just added all of those together. So the percent chlorine is going to be the total mass of chlorine in this molecule, which is 141.8 grams per mole, divided by the total mass of the formula, 203.8 grams per mole, times 100%. And this turns out to be 69.58%. Right? I'm using 4 sig figs in my answer because I used 4 sig figs from the periodic table. All right, the next example. What mass of iron 3 oxide contains 58 grams of iron? All right, it doesn't look like a percent mass calculation, but it essentially is. We could do it 2 ways, actually. So first we need to figure out what is the total mass of iron oxide. And to do that, we need to determine the formula of iron oxide. This is iron 3 oxide. So that means it's an iron 3 plus ion and an oxygen ion. So these 2 would combine, it would be Fe2O3. So 2 irons and 3 oxygens. So iron's atomic mass is 55.85, and I'm just getting these off the periodic table. And oxygen's atomic mass is 16.00. So the total mass of iron in iron oxide is iron 3 oxide is 111.7 grams. And the oxygen's total mass is 48.00 grams. So the total mass of 1 mole of iron oxide, 159.7 grams per mole. So we want to know what mass of iron oxide contains 58.7 grams. So we know that 159.7 grams contains 111.7 grams of iron. So we could do this as a cross multiplication problem. A lot of students prefer that method. And 159.7. All right, so if there's 111.7 grams of iron and 159 grams of iron oxide, then how many grams, then there's 58.7 grams of iron in how many grams of iron oxide. So that's our X. And we can do cross multiplication to solve for that, where we multiply these 2 and then divide by this one. And we could solve for X, and we would find that X equals 83.9 grams. So an 83.9 grams of iron 3, iron 3 oxide is Fe2O3. We would have a total of 58.7 grams of iron. The other way to do this is to figure out the percentage of iron. So I'll do this in a different color. We'll do it in green. So the percent iron would be 111.7 divided by 159.7 times 100%, which I did not pre-calculate, so I will do that right now. Need like the Jeopardy music playing. 111.7 divided by 159.7 times 100 is 69.94%. All right, so then we could do 58.7 grams divided by 0.6994, which is the percent as a decimal. 58.7 divided by 0.6994. Hey guys, I'm recording up here. Please quiet down. And we still get 83.9 grams. So either way would be kosher. You could do this via cross multiplication, or you can do this by figuring out the percent mass of iron and then figuring out 69.94% times X times what equals 58.7 grams. Let's do another problem. So the thing with the math in these chapters is there's, a dozen different ways a problem could be worded, or that they could ask you to find something. So I'm trying to work lots of example problems to show you this. All right, so this example problem here, if a compound is 42.65% silver by mass, then what mass of the compound contains 15 grams of silver? So 42.65% by mass silver. Say silver, Ag is silver. All right, that basically means that 42.65 grams of silver, that's gold, of silver are in 100 grams of the compound. That's what the percent means. 42.65% means 42.65 out of 100. So we can convert that percentage to a mass that we can use actually as a conversion factor, because now we have it in a ratio form. So if we have 15 grams of this compound, and we know that, actually I'm going to label this even a little bit clearer. If we have 15 grams of this compound, all right, and we know that for every 100 grams of this compound, there's 42.65 grams of silver. Our grams of compound cancel out. 15 times 42 divided by 100 is 35.2 grams. So in other words, you would need, nope, I did that wrong. Sorry, my bad. As we're not talking about 15 grams of the compound. Should read more carefully, Sarah. It says, what mass of the compound, that's what we're trying to find, contains 15 grams of silver? So if we have 15 grams of silver, I need to flip this conversion factor. I need my grams of silver on the bottom and my grams of compound on the top. That's why it's good to write out your units, make sure everything cancels properly. And the answer is indeed 35.2 grams. And that makes sense because the amount of compound should be greater than the amount of silver. Silver is a component of the compound. And that eyeballs about right too. 15 out of 35 is a little bit less than half, so about 42%. That checks out in terms of sort of mental math estimating and checking that the answer is correct. All right, here's another one. Determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. So if we're given a molecular formula, usually that means we need to figure out the molar mass. So aluminum, sulfur, and oxygen are the component elements here. There are 2 aluminums, and aluminum has a mass of 26.98 grams per mole. Sulfur, there's 3 sulfurs because there's 1 times 3. So 3 sulfurs, which are each 32.07 grams per mole. And then there are 12 oxygens because there's 4 times 3. So that's a total of 12 oxygens, which are 16.0 grams per mole. And now we calculate these totals and add them up. I didn't even calculate them out, but if we add them all together, it's a total mass of 341.8 grams per mole. Okay, so it's the molar mass of aluminum sulfate. So now we want to know what is the mass of oxygen in a 7.2 gram sample. So we can do this as a unit conversion problem. We have 7.2 grams of aluminum sulfate. All right, and that means that we can go to moles. So for 1 mole of aluminum sulfate, we have 1 mole of aluminum sulfate is 341.8 grams per mole. And in 1 mole of aluminum sulfate, we have 12 moles of oxygen, right? Total of 12 oxygens. And the mass of 1 mole of oxygen, is 16.00 grams. So our grams of aluminum sulfate cancel out. This should just say grams. Our moles of aluminum sulfate cancel out. Our moles of oxygen cancel out, and we're going to end up with grams of oxygen, the mass of oxygen. So 7.2 times 12 times 16 divided by 341.8 comes out to a nice even 4.0 grams of oxygen. So in a 7.2 gram sample of aluminum sulfate, there are 4.0 grams of oxygen. Another way to do this, and this is going to be true in chemistry, there's often more than one way to complete a problem. I prefer dimensional analysis because I'm good at it and I like dimensional analysis. But another way to do this is to use the percent mass. So I'm going to actually total this. 12 times 16. 12 times 16 is 192. So the mass of oxygen in this molecule is 192 grams per mole. So the percent oxygen is 192 divided by 341.8 times 100% divided by 341.8. That is equal to 56.17%. All right, so then we could take this number and we could say 56.17% times X equals, times our 7.2 gram sample equals what? that's going to be our mass of oxygen. So that would also equal 4.0 grams. Let me double check. Times 7.2. 4.0 grams, all right? So when you do this multiplication, though, you should use this, convert this percentage into a decimal. So it should be not 56.17 times 7.2, but 0.5617 times 7.2. So there's two ways to do it. One, using dimensional analysis and using the molar mass as a conversion factor and tabulating the number of oxygens per molecule. Or you can do it using the percentage, calculating the percent mass. Either way is valid, is totally kosher. All right, so when early chemists were determining chemical formulas from their experimental data, they went through these steps. So they broke apart chemicals, or they did chemical reactions, and they calculated the mass and therefore the moles of the different elements that they obtained, and then they were able to use that to determine the chemical formulas for these different compounds and substances they tested. So these are the steps that we're going to follow in these problems. First, we will start with either a mass of different elements, or the percent mass of each element in the substance. If we're given the percent mass, we're going to convert it to mass by just assuming that we have a 100-gram sample. And so we sort of did this before, and I'll show you how we're going to do it again. Step two is then we're going to take the mass of each element and determine moles. We can go from grams to moles using molar mass of the element. Then we're going to determine the mole ratios. In other words, we're going to divide all of the number of moles by the smallest number of moles in order to figure out what the ratio is between them. And then we might need to use a multiplier to turn those ratios into whole numbers. We ultimately want whole number ratios because the ratios are going to become the subscripts in our formula, and chemical formulas need to have whole numbers as subscripts. All right, so let's work an example problem. A compound is decomposed in a lab and produces 24.5 grams of nitrogen and 70.0 grams of oxygen. Find the empirical formula. So the first thing, so we're going to write out for nitrogen and for oxygen. So nitrogen, we get 24.5 grams of nitrogen. All right, we want to first determine, so we're starting with the mass, and now we want to determine the moles. So we can determine the moles by using the molar mass of nitrogen. 1 mole of nitrogen is 14.01 grams. So the number of moles of nitrogen is 1.75. All right, now for oxygen. The mass of oxygen that we have is 70.0 grams. We need to determine the number of moles by dividing by the molar mass of oxygen, which according to the periodic table is 16.0 grams per mole. Grams cancel out, and we end up with 4.38 moles of oxygen. Now we want to determine the mole ratios. We're going to do that by dividing both of these numbers by the smaller of the two. So we're going to divide them both by 1.75. That is going to equal 1. And 4.3 divided by 1.75 is 2.5. All right, 2.5 is not going to do. We need these to be whole numbers. So we need to multiply them both by the same number to get to a whole number. So 2.5 times 2 is 5. So we have to multiply the 1 by the same number. And so now we have whole number ratios. So 1 to 2.5, that is a ratio, but they're not whole numbers. So we multiply by 2 to get whole number ratios. So in other words, what this means is that there are 2 nitrogens and 5 oxygens in this formula. So the empirical formula is N2O5. That's what these mean. These are the subscripts in our formula. So that would be the empirical formula for this compound. Let's do another one. Ibuprofen, this is a painkiller, has the following mass percent composition. So it's made of carbon, hydrogen, and oxygen in the following percentages. What is the empirical formula of ibuprofen? We're doing the same steps. So I've got carbon, hydrogen, and oxygen. I want to start with the mass, but they give me a percent mass, so I'm just going to pretend that we have 100 grams of this. And if we have 100 grams of this, then that means we can convert all those percentages to grams, and we'll work as if we have, as if we're in grams. So for the carbon, 75.69 grams. We want to know how many moles is that. 1 mole of carbon is 12.01 grams. That's the molar mass. So we have 6.30 moles of carbon. Hydrogen, we have a mass of 8.80 grams. Divided by the molar mass, 1 mole is 1.008 grams. Grams cancel out, and we get 8.71 moles of hydrogen. And then for oxygen, our mass is 15.51 grams, divided by the molar mass of oxygen from the periodic table. Grams cancel out, and we end up with 0.97 moles of oxygen. So now the next step, and I'll do it in a different color to show we're doing the next step, is to divide all of these by the smallest one. So the smallest number of moles is 0.097. So we're going to divide them all by 0.097 to get a ratio. So this one equals 1. This one equals 8.98, which is so very close to 9. So we're just going to call that 9 as a whole number. And this top one, 6.3 divided by 0.97, is 6.49, which we can round to 6.5. All right, these are not whole number ratios because of that 6.5 there. So in order to get them to be whole numbers, I need to multiply them all by 2. So 6.5 times 2 is 13. 9 times 2 is 18, and 1 times 2 is 2. So our empirical formula for ibuprofen is, I'm going to pick some fun colors. Let's do purple. All right, so carbon has a subscript of 13, and hydrogen has a subscript of 18, and oxygen has a subscript of 2. These are the subscripts in our empirical formula. All right. So the empirical formula is remember the empirical formula, the definition of the empirical formula is it's the simplest ratio. All right, but it's not always the actual ratio. All right, the actual ratio is called the molecular formula. All right, and the molecular formula can be a multiple of the empirical formula. So just to refresh your memory from a previous lecture, glucose, all right, the molecular formula is C6H12O6. All right, but the empirical formula, the simplified version of this would just be CH2O. Okay, so the empirical formula is a simplified version, and the molecular formula for glucose is basically 6 times the empirical formula. So we can use experimental data to figure out the empirical formula, and we can find the molecular formula if we know the molar mass. So to find the molecular formula, we do need to know the molar mass. But if we have that, we can figure it out. We do that by first determining the empirical formula like we did above, and then determining the mass of that empirical formula just by, calculating the molar mass of it. If the empirical mass equals the molar mass, then the empirical formula is the molecular formula. All right, but if the empirical formula does not equal the molar mass of the compound, then we need to do a little division. We need to divide the molar mass by the empirical mass. And that will give us a number that we can use to multiply all of our subscripts by. Let's do a practice problem. A compound has an empirical formula of CH and a molar mass of 78.11 grams per mole. What is the molecular formula? All right, so we are given the empirical formula. We don't have to determine it, but we do need to determine the mass of this. So the molar mass of the empirical formula, CH, would be 12.01 grams per mole plus 1.008 grams per mole. So the empirical mass is 13.02 grams per mole. All right, that is not equal to 78.11 grams per mole, so we need to do some division. 78.11 grams per mole divided by 13.02 grams per mole is 6. So that means we need to take that CH and multiply it by 6. So our molecular formula would be C6H6, also known as hexane or cyclohexane is what it would be. All right, another example. In this one, we're going to have to determine the empirical formula because I can tell we're given some experimental data. Then we can figure out the molecular formula. A compound with the percent composition shown here has a molar mass of 60.10 grams per mole. Determine its molecular formula. Well, first we can figure out the empirical formula from the experimental data, just the way we were on the previous page. So we'll convert these percentages to grams, assuming that we have 100 grams, and 39.97 grams of carbon divided by the molar mass of carbon gives us 3.328 moles of carbon. And for hydrogen, 13.41 grams divided by the molar mass gives us 13.28 moles of hydrogen. And for nitrogen, 46.62 grams divided by 14.01 grams gives us 3.328 moles. The next step, of course, is to get the ratios by dividing by the smallest of these. So 2 of them are 3.328. We'll divide by 3.328. So the ratios are 1, 4, and 1. So they turn out to all be whole numbers. We don't need to use a multiplier. So in other words, our empirical formula is C1H4N1. So that is the empirical formula, CH4N. The molar mass of this empirical formula, the empirical formula mass, if we add this up, so it'd be 12 plus 4 plus 14, roughly, is 30.6 grams per mole. All right, 30.6 grams per mole does not equal that molar mass, so we need to do some division. So 60.10 grams per mole divided by 30.06 grams per mole equals 2. So basically we need to multiply the empirical formula by 2. So the molecular formula would be C2H8N2. We multiplied all of those subscripts by 2. All right, so we can only find the molecular formula if we are given the molar mass of the molecular formula. All right, so that's some calculating percent mass and figuring out and determining empirical formulas and even molecular formulas given molar mass. Now we're going to switch topics ever so slightly and talk about solutions. Not answers to problem solutions, but the chemical form of solutions, which are homogeneous mixtures of 2 or more chemicals. They can be any state of matter, so you can have a solid solution. That's an example of that would be metal alloys, like white gold in jewelry is gold with some silver or maybe even some nickel in it. Liquid is what we typically think of solutions as being liquid. Things like salt water, gasoline, coffee, juice, beer, all those things are liquid solutions. But then there's also air or gas solutions. Air, the air we breathe, is a solution. It's a homogeneous mixture of oxygen, nitrogen, hydrogen, well, not so much hydrogen, carbon dioxide. So a solution is made up of 2 parts, a solute and a solvent. The solute, excuse me, is the substance that is in the smaller amount, and the solvent is the substance that is the larger amount. I didn't mean to write substance. The solvent is present in a larger amount. All right, so in a white gold alloy, usually gold is the solvent, it's the larger amount, and then there's a small amount of some other metals that make it look more silver colored. In liquid solutions, in biology and often in chemistry, a very common solvent that we use is water. And because it's so common, we have a special term for solutions that use water as a solvent. We call them aqueous solutions. So most of the chemistry we'll be talking about are going to deal with aqueous solutions, where water is the solvent. Water is an excellent solvent for many reasons that we'll get to probably next semester. All right, so when we have a solution, we can measure the concentration of that solution. So concentration is a measure of how much solute is dissolved in a given amount of solution. We could write this out as a formula. We could say that concentration as an equation equals amount of solute per amount of solution. All right. But the thing is, this amount can be measured in different ways. We could measure the amount by mass. We could measure the amount by volume. We could measure the amount by number of moles. And so because of that, there are many different concentration units or ways of measuring concentration. So the 3 most common ones are molarity, percent, so we can do percent mass, percent volume, we'll see that, or parts per million or parts per billion. All right, we're going to walk through the math of calculating these 2. They are by far the most common. Alrighty, so the first one here, what is the molarity of a solution? Oh, I guess I should define molarity for you first in the space right here. So this first one, molarity, all right, which is also abbreviated with a capital M, all right. Molarity is defined as moles of solute over liters of solution. These are specific units, so it's not just moles per volume, it's moles specifically per liter. So the units of molarity, we oftentimes just write it as M, capital M for molar, but it means moles per liter. Alrighty, so what is the molarity of a solution that is 275 milliliters and contains 12.5 grams of sodium chloride? I always say start out by writing the formula. Write the formula that you're going to be using. And in this case, we're using molarity equals moles of solute per liter of solution. Okay, so do we have the moles of solute or the liters of solution? No, we need to find them. So first, let's find moles of solute. All right, we can do that because we're given the mass, and we can always convert from mass to moles by using the molar mass. So 12.5 grams of sodium chloride divided by the molar mass of sodium chloride. Sodium plus chloride, the molar mass, if we use the periodic table, we'll find it's 58.44 grams. So that is a total of 0.214 moles of sodium chloride, our solute. All right, check. We found the moles of solute. Now let's find liters of solution. All right, we are given 275 milliliters, all right, but we need it to be specifically in liters. So to convert this to liters, we're going to divide by 1,000 because there's 1,000 milliliters per liter. So converted to liters, that's 0.275 liters. Now we have our moles of solute and our liters of solution. So we can calculate the molarity. It is simply 0.214 moles divided by 0.275 liters, and that equals 0.778 moles per liter, or just M for molarity, 0.778 molar. That is the molarity of the solution. All right, molarity can also be a conversion factor. We can use it in a problem as a conversion factor because we can use it in those units of moles per liter, or we can flip that in liters per mole. So just like molar mass, grams per mole, is used a lot as a conversion factor, molarity, concentration, can also be used as a conversion factor. Let's do some more practice problems. How many milliliters of a 0.75 molar solution are needed to provide 1.25 moles of glucose, C6H12O6. So the first thing I like to do is sort of write out what we have. We have molarity, 0.750 molar, which we could also write out as moles per liter. And we're given 1.25 moles. And we want to know how many milliliters. That's what we're trying to figure out. Okay, so I'm looking at what we have, and I'm looking at the units. We have something in moles, and then we have something in moles per liter. So I could multiply these in order to convert from moles to volume of liters, and then I could easily convert from liters to milliliters. So that's what I'm going to do. I'm going to start with that 1.25 moles. I'm going to use the molarity as a conversion factor, and I'm going to flip it. So 0.750 moles per 1 liter. My moles will cancel out. Now I'm going to have units of liters, but I want units of milliliters. So I'm going to convert liters to milliliters. There's 1,000 milliliters in a liter. And this will tell me how many milliliters. So the answer, 1.25 divided by 0.75 times 1,000 is 1,670 milliliters. That's 3 sig figs green. 3 sig figs in my answer because I have 3 sig figs in the problem. In both of these numbers, there's 3 sig figs. Don't forget your sig figs. All right, next example. Determine the mass of sodium chloride needed to create 250 milliliters of a 0.35 molar solution. Again, I'm going to write out what I'm given. I'm given 250 milliliters and a 0.350 mole per liter solution. And I want to know the mass of sodium chloride. All right, so mass is in grams, but so far all I have are volumes and moles. So what's another way, what's something that can relate grams to moles? Ooh, molar mass. The molar mass of NaCl, I can calculate, is 58.44 grams per mole. So I have grams per mole, I have moles per liter, and I have milliliters. So I kind of just want to arrange these in a dimensional analysis problem so that my units all cancel out. I noticed that my units of volume are different. So in this conversion factor, it's in liters, but I'm given my volume in milliliters. So I want to go ahead and convert that to liters so that my units of volume can be the same. So 250 milliliters is 0.250 liters. All right. Generally, you want to start with whatever number is in single units and not ratio units, because the ratio units are ones that can be used as conversion factors. So that's where I'm going to start. I'm going to start with that volume of 0.25 liters. And now I'm going to multiply it by the molarity, 0.350 moles per liter. So my liters will cancel out. And now I can multiply this. I can use that molar mass to go from moles to grams. So 1 mole of sodium chloride is 58.44 grams. And now I will have an answer in grams. So we do the math here. We should end up with 5.11 grams of sodium chloride. In other words, if we want to make a 0.35 molar solution, this is supposed to be my flask, all right, we need to add 5.11 grams of sodium chloride and then bring it up to a volume of 250 milliliters with water, and we would end up with a 0.35 molar solution of sodium chloride. So this is the type of calculation that scientists in labs do all the time when they are making solutions of certain concentrations. They have to figure out what mass of their solute to weigh out in order to make a solution of the correct concentration. And you will be doing this in an upcoming lab. You'll be performing some calculations to make solutions of certain concentrations, and then you'll actually make them. Alrighty, so another thing that we might want to do is take a stock solution, a concentrated solution, and dilute it to make solutions that way. So dilutions are a very common thing that's done in preparation, lab preparation in science. Rather than having to make a bunch of different solutions by measuring out different masses of sodium chloride, you might make a master stock solution, what we call a concentrated stock solution, and then you can dilute it and make different lighter concentrations. So a dilution, basically what you're doing in a dilution is you're adding more solvent, so you're increasing the volume, but you're not changing the amount of solute. So the moles of solute stay the same, but the volume goes up. And so the concentration goes down. So in a concentrated stock solution, the number of moles, N, is going to represent the number of moles, is the molar mass, the molarity, or I'm going to say the concentration, C, times the volume. All right, we're going to call this C1V1. And where N equals the moles of solute. All right, in the diluted solution, you've added more volume, all right, but the number of moles is still the same. The concentration has gone down and the volume has gone up. And so the number of moles is still going to be the same, but we're going to have a new concentration and a new volume. Okay, so when we are doing dilutions, we can use this very handy formula that we derive from this equivalency here. The number of moles stays the same, then that means the concentration of the stock solution times the volume of the stock solution that you use will equal the final concentration of our diluted solution times the final volume. C1V1 equals C2V2. We call this the dilution equation. And whenever you have a dilution problem, this is the formula that you want to use. C1V1 equals C2V2. Sometimes you'll see it written as M1V1 equals M2V2, where M stands for molarity. All right, but the concentration does not have to be in molarity. It can be in any unit. So I prefer this more universal form. So just to map it out, C equals concentration, and V equals volume. All right. By definition, all right, the stock solution, the initial concentration is going to be greater than the final concentration. By definition, when you're doing a dilution, you're reducing the concentration. Also, by definition, you're increasing the volume. So the second volume, the final volume, is going to be higher than the initial volume. And these are things to remember when you are mapping out these word problems. Because a lot of times the mistakes people make is they can't properly identify which is the initial concentration or the final concentration, which is the initial volume and which is the final volume. But if you keep this in mind, this will help you make sure that you are identifying things properly. So by definition, this is true because concentration decreases in a dilution and volume increases. Another thing about this formula here, the dilution formula, is that the units are not important. The units don't matter as long as they match. So in other words, it doesn't matter whether your volume is in liters or milliliters or cups or fluid ounces. It doesn't matter as long as you're using the same units for both. So as long as your initial volume is in fluid ounces and your final volume is in fluid ounces, it doesn't matter. Unlike when we're calculating molarity, molarity very specifically needs to be in a volume of liters, okay? But for calculating dilutions, it does not matter what the units of volume and concentration are as long as they match before and after. So let's work some practice problems. What is the molarity of a diluted solution if 250 milliliters of a 2 molar hydrochloric acid is diluted to 1200 milliliters? All right, so I've sort of mapped this out already. We need to figure out what is our initial concentration and volume and our final concentration and volume. So, and we know it's a dilution problem because it says diluted. So we know that automatically we need to use this formula. C1V1 equals C2V2. That's why I've written all those components out right there. The molarity of the diluted solution if 250 milliliters All right, I'm just going to look. I'm not even going to read the problem. I'm just going to look at the numbers here. So I have two volumes, 250 milliliters and 1200 milliliters. Okay, by definition, when we do a dilution, the volume is going up. So I know that the larger volume must be my V2, my final volume. And the smaller volume is my initial volume. All right, and so now I need to figure out whether this 2 molar is the initial concentration or the final concentration. Well, it says we have 250 milliliters of 2 molar. And since this is the V1, then this must be the initial concentration. So 2.00 molar. So that means C2 is the variable that we are solving for. So C1V1, so 2.00 molar times 250 milliliters equals C2, that's our mystery variable, times V2, 1200 milliliters. So to solve for C2, I need to divide both sides by 1200 milliliters. Oh, and look at me, I didn't even do the work in my notes. So that cancels out, and now I've got to do some math in my calculator. 2 times 250 divided by 1200 equals, so C2 equals 0.417, is that right? That doesn't seem right. 2 times 250 divided by 1200. Nope, that's right. So 0.417 milliliters is all I need. Or is the concentration? Nope, sorry. This is a concentration. It's not going to be in milliliters. It's going to be in molarity. All right, so the molarity, the concentration of the final solution is going to be 0.417 molar. And this makes sense. We would expect it to be less than 2 because the concentration is going down. We're diluting it. So if this number came out to be greater than 2, that would be a problem. All right, let's do another one. What volume of water should you add to dilute 0.2 liters of a 15 molar sodium hydroxide solution to obtain a 3 molar sodium hydroxide solution? So it says, what volume of water should you add to dilute? That word dilute tells me this is a dilution problem. I'm using C1V1 equals C2V2. So I've got those mapped out here, and I'm going to plug those in. So I have two concentrations, 15 molar and 3 molar. So in a dilution, the concentration's going down. So I know the higher concentration is my initial, and the lower concentration is my final. And I've got 0.2 liters of that initial. So my initial volume is 0.200 liters. So I don't know the final volume. So that I need to solve for. So C1, 15.0 molar, times V1, 0.200 liters, equals C2, 3.00 molar, times V2, which I don't know. Divide both sides by 3.00 molar. And that cancels out. The molarity cancels out. So 15 times 0.2 divided by 3. 15 divided by 3 times 0.2 equals 1. So our volume, our final volume, equals 1 exactly. I want it to be 3 sig figs though, 1.00 liters. My units now of volume is liters. But it doesn't ask you what is the final volume of the solution. It says what volume of water should you add. All right, so if I want the final volume to be 1.00 liters, all right, then the amount of water is going to be that final volume minus the initial volume. So in other words, 1.00 liters minus 0.200 liters. So that means I need to add 0.800 liters of water in order to get a final volume of V2. So this question had that extra twist. It didn't ask you to solve the final volume. You had to solve the final volume, but it was asking you what volume of water did you need to add to get there. And that's simply, to figure that out, you just do the final volume minus the initial volume to figure out how much volume of water you need to add. All right, one more. What volume of a 30% glucose solution should you use to make 0.500 liters of a 5% solution? So in this case, it gave us concentration as a percentage. So our concentration, the higher concentration is going to be our initial, the 30%, and the final concentration, we want to dilute it to 5%, and we want to make 0.5 liters of that 5% solution. So that's the volume of our diluted solution. And we want to know what volume of that stock solution, what is the initial volume. So C1, 30% times V1, which we don't know, and C2, 5% times V2, 0.500 liters. Right, we're going to divide both sides by 30%. And that cancels out, so we can solve for V1. The percents cancel out, so it doesn't matter that we were in percent and not molarity. And 5 times 0.5 divided by 30 equals 0.083. And I just want 2 sig figs because this number here is only 2 sig figs. So 0.83, and my units that I have left are liters. So I want to use 0.083 liters of the stock solution in order to make 0.5 liters of the diluted solution. All right, so if I was making this solution, in other words, all right, I would take, if here's my stock solution, all right, I would need to measure out with a pipette. This is my pipette and my bowl. It's not very good. All right, I would need to measure out 0.083 liters, which is 83 milliliters. And then I would transfer that into here, very small amount. And then I would bring it up to 500 milliliters or 0.5 liters with water, and that would give me a 5% solution. All right, so in that last problem, it mentioned percent mass. The concentration was in percent. So we can talk about concentration as a percentage. We would call it percent concentration. That annoying bird sound is my husband's hawk. He's a falconer. Fun fact for you, and he has a Finnish goshawk that lives in our backyard, and it's really annoying and noisy. Okay, so percent mass is when you have the mass of the solute divided by the mass of the solution. There's also percent by volume, where you are measuring the volume of the solute divided by the volume of the solution. Or you could calculate percent as a percent mass by volume, where you calculate the mass of the solute divided by the volume of the solution. So there's sort of 3 different percent concentrations, and in the problem it should specify that. So percent mass is often written as percent by mass, it'll say either percent by mass, or it'll say percent m divided by m, mass divided by mass, and so on and so forth. So let's do a practice problem. We have a 5-gram sample of spinal fluid, and it contains 3.75 milligrams of glucose. What is the percent by mass of glucose in spinal fluid? So the first thing you want to do is really write out that formula that you're going to use. Percent mass equals the mass of solute, in this case glucose, divided by the mass of the solution. In this case, the solution is the spinal fluid. And all of it times 100%. So let's write out these different components. We've got percent mass. We need the mass of the solute, so the mass of the glucose. And we need the mass of the spinal fluid, which is the solution. So we don't know the percent mass. That's what we're trying to find out. The mass of the glucose is 3.75 milligrams, and the mass of the spinal fluid is 5.0 grams. All right, so we have everything we need. The only problem is we really need these units to match up. So it doesn't really matter which mass units we use or which volume units we use if it's percent volume, but they do need to match. So I can either change the 5 grams to milligrams, or I can change the 3.75 milligrams to grams. I'm going to change these to grams. I'm going to do that by dividing by 1,000, because there's 1,000 milligrams in a gram. So 3.75 milligrams divided by 1,000, 0.00375 grams. Okay, so now I have my mass of glucose and my mass of spinal fluid, so I can solve the percent mass. The percent mass is going to be 0.00375 grams divided by 5.0 grams times 100%. And this turns out to be a very small percentage of 0.075%. So if this is true of spinal fluid, then it is 0.075% glucose. Do another practice problem. Concentrated hydrochloric acid is actually an aqueous solution that is 37.2% by mass of hydrochloric acid. And that's what, when we use hydrochloric acid as a lab reagent, that's what concentrated hydrochloric acid is. It's not actually pure HCl, it's a solution. The density of this solution is 1.19 grams per milliliter. What mass of hydrochloric acid is contained in 0.5 liters of this solution? So I'm going to start by sort of writing out all of the components. So first, we've got the percent mass. So we know the percent mass is 37.2%. We are given a density of 1.19 grams per milliliter. And we want to know what mass, we want to know the mass of HCl. That's what it's asking us for. That's our question mark. And it gives us a volume of solution. So a volume of solution is 0.500 liters. All right. We know that percent mass is the mass of the solute. In this case, HCl is our solute. We don't know what that is. All right, that's actually what we're trying to find. And it's also, so I'm going to actually just move that up there. So our mass of HCl, that's what we're ultimately trying to find, divided by the mass of the solution. All right, which we also don't know. That's a blank. Okay, but we know the percent mass of the solution, So we know one part of that equation. Could we figure out what the mass of the solution is with the information we're given? We're given a volume and we're given a density. And density happens to be a conversion factor we can use to convert between volume and mass. So we could figure out the mass of the solution using those two. So the mass of the solution up here is going to be the volume of the solution times the density. That will give us the mass of the solution. Now, I notice that my volume of solution is in liters, the unit of volume and density is in milliliters. So I want to make those match first. So I'm going to convert this one from liters to milliliters. So 5 liters is 500 milliliters. So that when I do this math, my units cancel out. So 500 milliliters times 1.19 grams per milliliter is a mass, means my mass of solution is 500 times 1.19, 595 grams. All right, so I have, if I write out the formula for percent mass, equals mass of solute over mass of solution times 100%. All right, I know the percent mass, and I just solved the mass of the solution. So now I can solve for this variable here, the mass of the solute, and that's ultimately what we want to find. So if I plug in what I have, 37.2% equals X, we don't know the mass of the solute, divided by 595 grams of solution times 100%. And now I can solve for X. I'm going to multiply both sides of the equation by 595 grams over 100%. 595 grams, 100%. So I multiply both sides of the equation by the same thing. I cancel out everything on this side of the equation, so I have X by itself. My percents cancel out, and X, the units of X is going to be grams. So 595 times 37.2 divided by 100 equals 221.34, but I want my answer in 3 sig figs, so 221 is where I will end it. So 221 grams. In other words, there are 221 grams of HCl in half a liter of this solution. More practice problems. We're going to just keep them going. All right, and this one we've got rubbing alcohol is usually sold as a 70% by volume aqueous solution. If the density of isopropyl alcohol is 0.785 grams per milliliter, how many grams of isopropyl alcohol are present in 355 milliliter bottle of rubbing alcohol? I'm going to start by writing out what I have. I have a percent by volume. The percent by volume is 70%. And I have a density of 0.785 grams per milliliter. And I have a volume. This is a volume of the solution specifically, and that's 355 milliliters. All right, the percent volume per volume equation is volume of solute divided by volume of solution times 100%. All right, and I want to know, it's asking me how many grams of isopropyl alcohol. how many grams of isopropyl alcohol. Isopropyl alcohol here is the solute. All right, that's what we want to know. Ultimately, we want a mass of solute. All right, there's no mass of solute in this equation. So that's throwing me. But what do I have? Let's start there. What do I have and what can I do with it? So I have this percent volume, and I have the volume of the solution, so I could find the volume of the solute, so I'm going to start with that. It doesn't tell me, I want to know the grams of the solute ultimately, but if I can't figure out how to do that right away, I'm going to solve what I can. So first I'm going to solve for the volume here. So that's my first step. So I'm going to plug in the 70%, and I don't know the volume of the solute, but I do know the volume of the solution is 355 milliliters. So I'm going to multiply both sides of the equation by 355 milliliters over 100%, because that's going to allow me to cancel out those and solve for x. So 355 times 70 divided by 100 is 248.5. So x is 248.5 milliliters. My percents cancel out, and I'm solving for that volume. So this is the volume of the solute, which is the isopropyl alcohol. And if I want to find the grams, I want to go from volume to grams. Well, I have this density here, and density, conveniently, is a conversion factor between volume and mass. So I can use that. I can take my 248.5 milliliters, and I can divide it by the density, 0.785. Nope, I did that backwards. I'm going to multiply it by the density. This is why I like dimensional analysis, because I can realize when my units aren't canceling out. So 0.785 grams per milliliter. My milliliters cancel out, and I will end up with a mass in grams. 248.5 times 0.785 equals 195 and change, but I want my answer to have 3 sig figs, so 195 grams. That is the mass of isopropyl alcohol that's in rubbing alcohol, a solution of rubbing alcohol that's 355 milliliters. Alrighty, so we've learned these different concentration units, molarity and percentages. Sometimes questions might ask you to convert between the two. So you might be given a concentration in percent and asked to convert to molarity, or vice versa. So let's work some practice problems. Converting between concentration units. Here we have a hydrochloric acid solution. It's 26% HCl by mass, and it has a density of 1.125 grams per milliliter. And we want to know what is the molarity. So I'm just going to map out what we have. We have the percent mass by mass is 26%. All right, so that equation involves the mass of solute divided by the mass of solution. So I'm just going to map that out because I might need that. Okay, I don't know what those are. They're not given in the problem. We're also given a density. The density is 1.125 grams per milliliter. And we want to know what is the molarity. In other words, we need to know how many moles. And per liter. Okay, so we have a 26% solution. It doesn't matter what volume, how much of this solution we have. We just need to work with some amount of this solution. So in this case, what we do is, let's just say that we have 100 grams of this solution. If that's the case, then that means that if it's 26%, then 26 grams of that solution are the solute. So we can pick this sort of arbitrary amount. 100 grams is easy to work with, so that's why we pick that amount. Okay, so if we have 100 grams of solution and 26 grams of solute, we can now figure out the moles of solute and the liters of solution. So the mass of the solute, we can figure out how many moles of solute we have using the molar mass. And the molar mass of HCl is, if we look that up, it's 1.08. 1.008 is hydrogen plus 35.45 is the mass of chlorine. So that molar mass is 36.458 grams. So 26 divided by 36.458 is 0.71315 moles. I'm carrying this out extra figures because I'm not done yet. So I don't want to round it until I get to the end of the problem. So I want to use extra sig figs throughout my calculations. Okay, so now I've figured out how many moles. That's useful. So I'm going to say 7.71. I'm just going to make myself a little bit more room here. So I'm going to say that molarity is moles per liter. So we just, moles of solute, more specifically, moles of solute per liters of solution. So I just solved for the moles of solute. That's 0.71315. And now I need to figure out how many liters of solution I have. Well, I can do that because I have a mass of the solution and I have the density of the solution. So I can use the density to figure out the volume of solution. So I can say that 100 grams times, or divided by 1.125 grams per milliliter equals a volume of 88.8888 milliliters. All right, but I need the denominator here to be specifically in liters. So I'm going to convert that to liters by dividing by 1,000, 0.08889. Ah, what did I do? Here we go, 8889 liters. So now I can plug that in down here, 0.08889 liters. And now I can solve for molarity because it's moles per liter. So 0.71315 divided by 0.08889 is 8.0228, but this question I'm given 2 sig figs in that, so I want my answer to be in 2 sig figs. So my answer is just going to be 8.0 molar, or 8.0 moles per liter, either one. And that is the molarity of a 26% HCl solution. Let's do one more. This one we're going from molarity to percent. We're going the other way. So we have a 4.5 molar solution. So I'm going to write 4.50 moles per liter because when I write it out like that, I know I can use it as a conversion factor, of calcium chloride. And it has a density of 1.392 grams per milliliter, another potential conversion factor. And I want to know what is the percent by mass of the solution. That's what I'm trying to find. So the percent by mass is going to be the mass of the solute divided by the mass of the solution. All right, I don't know the mass of the solute or the mass of the solution times 100%. But I need to figure them out in order to figure out the percent mass. So what I don't have is it didn't give me an amount of this solution. But it doesn't matter what amount of solution I have, because no matter what volume of solution I have, it's going to be the same concentration. So I can pick an amount, kind of like I did before when I said, oh, let's pretend like we have 100 grams of this solution, and we can work from that. So we can do that here as well. We can pick an amount. So we could pick 100 grams. Or what we could do, since we're starting with molarity, is I find it's easier to pick a volume. So let's say that we have 1 liter. Let's pretend we have 1 liter of solution. All right? So now we have a volume of 1 liter, volume of solution. All right, so if we want to figure out the mass of the solution, we can do that because we know the density. So if we have 1 liter of solution, we can figure out the mass of the solution to plug it in here. So the mass of the solution, I'm going to write that up here. All right, we can figure out the mass of the solution because it's going to be the volume times the density. So we have 1 liter, which is 1,000 milliliters, times the density of 1.392 grams per milliliter. So our mass of solution, 1,000 times 1.392. I don't know why I typed that into my calculator. That was silly. It's 1,392 grams. So that's our mass of solution. We've got that now. Check. Now we need to figure out the mass of the solute. How can we do that? Well, we have a molarity, and the molarity tells us the moles per liter, so we could figure out how many moles of solute we have. And then if we know the moles, we can always figure out the mass because we can use molar mass. So that's what we're going to do. We have 1 liter of solution, and we know that there's 4.5 moles in every liter of solution. So that means that we have 4.5 moles of our solute. And to figure out the mass of the solute, we're going to take that 4.5 moles and multiply it by the molar mass. What is our solute here? Our solute is calcium chloride. Calcium chloride is CaCl2. Calcium has a 2+ charge. Chloride has a 1- charge. So CaCl2. So 1 mole of CaCl2. We got to use our periodic table here to figure out the molar mass. So the molar mass of CaCl2 is, again, it would be helpful if I had calculated this beforehand. All right, calcium is 40.078, and chlorine is 35.45, and there's 2 of them. So the molar mass of calcium chloride is 110.98 grams per mole. So 1 mole is 110.98 grams times 4.5 moles Our moles cancel out, and that means we have 499.4 grams of our solute calcium chloride. So we want to know the percent mass. We now have the mass of the solute and the mass of the solution, so we can do that. The percent mass is the mass of the solute, which we just calculated is 499.4 grams, divided by the mass of the solution, which we calculated up here, 1392 grams, times 100%. And that equals 35.9%. I round it to 3 sig figs because I have 3 sig figs in this number here, so I want 3 sig figs in my answer. So a 4.5 molar calcium chloride solution is 35.9% calcium chloride by mass. All right, so practice these. Come to study group or office hours if you have questions.